Yeah, good afternoon, students. Welcome you all to the session. So I hope I am visible and audible to all of you. So yeah, yes, okay. So today we are going to see a new topic, that is electrochemistry, and let us revise this electrochemistry with a few topics. Let me give you a gist of it, and then we will solve some questions related to this electrochemistry. Okay. So the topics that we are going to see, or the very important topics in this lesson, are the introduction and the types of electrochemical cells, and we will see what is electrode potential, EMF of a cell, Nernst equation, Gibbs free energy and EMF relation, Faraday's laws, electrolytic conductance, and Cold-Roche law. So all these topics we will cover here in this session, and then we will solve the questions, problems related to all these talks. Okay. Now moving on to the introduction. So what is an electrochemistry? So it is a branch of physical chemistry which deals with the study of interconversion of chemical energy and electrical energy. Okay, it is a study of interconversion of chemical energy and electrical energy. That's why the name is called as electrochemistry. Got it? And we have two types of electrochemical cells. One is galvanic or voltaic cell, and the other one is electrolytic cell. And galvanic cell, as you can see here, it converts chemical energy to electrical energy, whereas electrolytic cell is converting electrical energy to chemical energy. And here the continuous redox reaction occurs, and here the redox reaction is non-spontaneous in nature. Got it? Now, discussing about the each electrochemical cell separately. So I'll go with the galvanic cell first, which is otherwise called as voltaic cell. So the example for the cell is Daniel cell. Okay. So in the Daniel cell, we have two beakers, and zinc electrode is dipped in the first beaker, and copper electrode is dipped in the copper sulfate solution. And the salt bridge is connecting these two solutions, and it is connected to the circuit. And in this particular zinc sulfate solution, you can see the zinc is getting oxidized and the copper is getting reduced here in the other beaker. So oxidation, both oxidation and reduction happens here. And oxidation always occurs in anode, and reduction always occurs in cathode. So the flow of electron is from zinc. Here you can see the flow of electron is from zinc to copper. Current is flowing in the opposite direction from copper to zinc. Got it? The flow of current will always be opposite in direction to the flow of electrons, right? So the anode in anode we have oxidation, in cathode reduction occurs. And how to represent this particular oxidation reduction in a representation? So that representation is called as cell representation. Here we have to denote the element which is getting oxidized first, that is zinc is getting oxidized. So zinc is getting oxidized to zinc 2 plus by losing 2 electrons, and this reaction occurs in anode. So you have to separate these two species with a line. Okay. And in the same way, cathode reduction occurs in cathode, and copper 2 plus is getting reduced to copper. And this cathode and anodic, these two species has to be separated by a parallel line, by putting a parallel line, and that denotes the salt bridge. And the separate half reaction, oxidation half reaction, reduction half reaction you can see, and this is the overall redox reaction in which the zinc is getting oxidized and the copper is getting reduced. Got it? So this is about the galvanic cell. And coming to the electrode potential. Electrode potential is the potential difference between the electrode and the electrolyte due to the separation of charges is called as electrode potential. So electrolyte means it is an electrolytic solution. So there will be the potential between for electrolyte as well as for electrode. The difference in the potential is called as electrode potential. So we call them as oxidation potential and reduction potential. Standard electrode potential, that is E naught. Standard electrode potential is represented by the symbol E naught, and it represents the potential at 298 Kelvin and at 1 bar pressure and 1 molar concentration. So if the pressure is 298 Kelvin, if the temperature is 298 Kelvin, if the pressure is 1 bar and if the concentration is 1 molar, then we can tell that electrode potential as standard electrode potential because it is in the standard condition. Okay. And let me discuss more in detail about this oxidation and reduction potential. So oxidation potential, the electrode potential for oxidation half reaction is called as oxidation potential. You can see the general reaction there. And if that oxidation potential is more, greater will be the tendency to get oxidized. If the value is more, then the element can get oxidized easily. And if the reduction potential value is greater, then the element can get reduced easily. Element can easily gain the electron and can get reduced. So higher the values, higher is the tendency to get oxidized and reduced. Got it? So this is about this oxidation and reduction potential. Then next I will see the electromotive force of a cell. That is EMF. Okay. So the difference in the electrode potential of the two electrodes of the cell is termed as electromotive force of the cell or cell voltage. So we have two electrodes and both the electrodes have some electrode potential. The difference between those two electrodes will give this EMF. And it is calculated using three formulas. Okay. Reduction potential of cathode minus reduction potential of anode, or oxidation potential of anode minus oxidation potential of cathode, oxidation potential of anode plus reduction potential of cathode. So all these three formulas you can note it down. Very important formula. So we will use the corresponding formula for the respective problems. Then I will discuss the electrochemical series. So this is a series in which the elements, the ions are placed from the more oxidizing nature to the least oxidizing nature. Okay, you can see this here. In the first row we have fluorine, next we have lead, chlorine, water, etc. And fluorine is having the strongest oxidizing nature. Okay, you can see it is more positive. It is plus 2.87, right? So it is having the highest, more positive value. So it has the more oxidizing power. So it is the weakest reducing agent. When you come to the bottom, it is lithium. Lithium is having the more negative value of this standard potential. So it is the strongest reducing agent and the weakest oxidizing agent. Okay. So the elements, ions are arranged in an increasing order of their reducing nature or oxidizing nature, we can say. And that series is called as electrochemical series. Okay. Now moving on to the next thing, that is Nernst equation. We have three formulas for Nernst equation. So first, for electrode, that is if an ion is gaining some electron and if it is getting converted to a metal, okay. So then the Nernst equation for such type of electrode species is E is equal to E naught cell minus RT by NF Ln concentration of the metal by the concentration of the metal ion. Okay. So here the R value is 8.314 joule per Kelvin per mole and Faraday's constant is 96,500 coulomb. And for the cell, for a particular reaction A plus BB giving CC plus DD, this particular Ln concentration value, it is getting converted to log Q. It is getting converted to log Q, where Q is equal to concentration of C to the power C into concentration of D to the power D by concentration of A to the power A by concentration of B to the power B. This is nothing but Q. Okay. Now at equilibrium, E cell is going to become 0. If E cell is going to become 0, E naught cell will be there and take this whole term to the other side. It will be equal to 0.059 by N into log K. At equilibrium, Q is getting changed to K. So it is an equilibrium constant, right? So we are putting K in place of Q. So these three are the Nernst equations which you have to memorize. And N denotes the number of electrons lost or gained in a reaction. N denotes the number of electrons lost or gained in a reaction. Fine. Now we will see one more relation between Gibbs free energy and EMF. So delta G naught, the change in the Gibbs free energy is equal to minus NF E naught cell. Very important relation. And if you want to relate Gibbs free energy with Kc, equilibrium constant, then go for this relation, minus 2.303 RT log Kc. Okay. If the E naught cell, if this E naught cell value is positive, then minus into plus becomes minus, right? So delta G becomes negative. If delta G is negative, then the reaction is spontaneous. Always remember, if the delta G is negative, then the reaction is spontaneous. If it is positive, then the reaction is always non-spontaneous. If delta G is equal to 0, then the reaction is at equilibrium. Okay? Very important conditions you have to memorize. The next, we will study the Faraday's laws. So we have two laws. The first law says that mass of any substance produced should be proportional to the amount of current passed. M is the mass of the substance, I is the current. Okay, so it is both are directly proportional. So how many the amount of current you are passing, so that is proportional to the mass of the substance. Okay, and the second law says that the amount of the substance produced by passing electricity will be proportional to their chemical equivalent weight. If the number of chemical weight is more, then the amount of substance produced by passing electricity will also be more. So W is the weight and E is the equivalent. Got it? So these are the two Faraday's laws. And moving on to electrolytic conductance topic. So we are going to see 6 formulas here. First 3 are there in the screen for you. So first formula is resistance. Resistance is equal to V by I. Okay. And conductance is denoted by G. Conductance is the opposite, reciprocal of resistance, right? So G is equal to 1 by R. And coming to the specific resistance is otherwise called as resistivity. So we know that R is equal to rho L by A. So rho, that is resistivity, is equal to RA by L. So you have to learn this formula where A is area of the electrode and L is the distance between the two electrodes in the electrolytic cell. Okay. This is the specific resistance formula. And coming to the specific conductance or conductivity, denoted by the letter kappa. So this is called as kappa. So resistance is the opposite of conductance. The same way, this conductivity is the opposite of resistivity, right? So kappa is equal to 1 by rho. So we know that 1 by rho is equal to this thing, okay? Cell constant. This L by A is the cell constant into G. Okay, this formula you are studying. And molar conductance, lambda M, is equal to kappa into 1000 by M, which 1 mole of the substance is giving, no? So it is 1 by M. And for equivalent conductance, it is 1000 by N. N denotes the number of gram equivalent for the substance. So lambda EQ is equal to kappa into 1000 by N. Okay. So these are the 6 formulas you are going to study from the electrolytic conductance topic. Now next I will discuss the effect of dilution on electrolytic conductance. So when I dilute the solution, what is going to happen? What is going to happen for the conductance? Conductance also increases. Okay. When we increase the dilution, conductance also increases. For strong electrolyte with dilution, strong electrolyte in the sense strong acid or strong base, for them, if you increase the dilution, the interionic force of attraction decreases because ions are going to get separated easily. So what happens? More number of ions will move in the solution. So more number of movement of ions inside the solution increases the conductivity. Okay, so that's why the conductance increases. And for weak electrolyte, weak acid, for weak base, the separation of ions is partial. So on increasing the dilution, degree of dissociation, that power increases, conductance increases. So in both the case, conductance is going to increase, but with different reason. So here in the first case, due to the less interionic force of interaction, and here due to the more degree of dissociation. Okay. Now, with dilution, specific conductance decreases. Kappa, conductivity decreases because with dilution, the number of ions in 1 centimeter cube solution decrease. Conductivity increases, but conductance decreases. Okay, so you can see here, this is a concentrated solution. So in which for 1 centimeter cube of area, more number of ions will be there. You can see. And in case of diluted solution, the number of ions per unit volume is very less. Very less number of ions are there. So if only very less number of ions are there, movement of ion is very less. So the conductance is getting decreased. Okay. So with dilution, equivalent and molar conductance, that are lambda EQ and lambda M, both of them increases because with dilution, normality and molarity decreases because the number of moles of the solute decrease. If the number of moles of the solute decrease, molarity and normality involves those number of moles of solute, right? So that is going to decrease. So molarity, normality decreases and the volume increases. Got it? So on this point, just keep on revise it and keep in mind. Now next we will study the determination of molar conductance at infinite dilution. Determination of molar conductance at infinite dilution, which is denoted by d by Huckel-Onsager equation. So we are plotting a graph between the concentration and the molar conductivity. Okay. So here we are getting a graph and we are getting a curve. The curve denotes the weak electrolyte curve and this line is the KCl. KCl is a strong electrolyte. For strong electrolyte, we are getting a line, and for weak electrolyte, we are getting a curve. And if we want to write the equation, it is lambda m is equal to lambda m naught minus A into C power 1 by 2. And this equation is only for strong electrolyte. So in which it is in the formula y is equal to mx. So here is the mx and this is the C part, mx plus C. So where y-axis is lambda m and x is C power 1 by 2. M is the slope and slope is A here. Okay, and lambda m naught is the intercept. Okay, so here is the intercept only for strong electrolyte. So this is the intercept and this value is lambda m naught, and if I take the slope of this line, I will get A. Okay, so this is the equation from which we are getting this type of curve. Got it? You can find out the molar conductance at infinite dilution using this curve, using this graph. Now next I will discuss the Kohlrausch law. Okay, it is also called as independent migration of ions law, and this law states that the equivalent conductivity of any electrolyte at infinite dilution is the sum of equivalent ionic conductivities of cation and anion given by the electrolytes at infinite dilution. So, okay, it is given by lambda m naught or lambda EQ, which is equal to the nu plus, those nu plus and minus represents the stoichiometry of ions dissociated, and lambda is the limiting molar conductivity. Suppose if I am having NaCl, okay, so here this NaCl will be separated into Na plus ion and Cl minus ion. Okay, so if I am having MgCl2, so it will get separated like Mg2 plus and 2Cl minus. So here this 1 and 2. So they represents this nu plus and nu minus. Okay. And lambda m naught is the limiting molar conductivity that will be given in the question. And this is the Kohlrausch law, which is being used for the thing to calculate the molar conductivity at infinite dilution. Now the applications, what are the things we can get from this Kohlrausch law? Degree of dissociation of weak electrolyte can be found out, that is alpha, by using lambda mc, that is molar conductance, divided by molar conductance at infinite dilution. Molar conductance at concentration C by molar conductance at infinite dilution, and or zero concentration. Okay, by using this formula, you can find out the degree of dissociation. And secondly, we can find out the Kc, that is equilibrium constant. Dissociation constant we can get for weak electrolyte. When AB is dissociated to A plus and B minus, initially the concentration of AB will be C, and for A plus and B minus, it is 0. Now at equilibrium, C alpha moles is produced, and here also C alpha moles of B minus is there, and C minus C alpha is the concentration at equilibrium for AB. Now if you substitute in the equation, that is Kc will be equal to the concentration of A plus into the concentration of A minus divided by the concentration of AB, right? So when we substitute, we will get this relation, and on calculation, we will get C alpha square by 1 minus alpha. So we can get this, and we can get some more things also that we can discuss with in the questions. Got it? So this is the very small gist of this electrochemistry topic. So go through all the formulas which I have given you in this: Faraday's law, Kohlrausch law, electrolytic conductance, in that resistivity, conductivity, resistance, conductance, all the things you go through. Nernst equation, which is very important. So all those topics, formulas, you study and try to solve questions on this. And now in this session, we will try to cover as much question as possible. Okay. Previous year's questions we will do on JEE and NEET for electrochemistry. Yeah. So here is the question for you. The E0 values for aluminium plus aluminium and thallium plus thallium, it is given. We have to identify the incorrect statement. We have to identify the incorrect statement. Whether aluminium is more electropositive than thallium, or Tl3 plus is a good reducing agent than Tl plus. So we have to find out whether aluminium plus is unstable, or thallium can be easily oxidized to thallium 3 plus from 1 plus. So which statement is incorrect? So here, option B is the correct answer, because we know on moving down the group, inert pair effect is observed for the elements. So on moving down the group, the higher members are stable at very low oxidation state. Okay, means thallium plus is more stable. Thallium plus is more stable than thallium 3 plus. So what is meant by oxidizing and reducing agent? Oxidizing agent means it will go and accept the electron from the species to which is getting reacted. Okay. Thallium 3 plus is an oxidizing agent. Thallium 3 plus is an oxidizing agent. It will take 2 electrons, it will accept 2 electrons, and it will try to convert it to thallium plus, because thallium plus is more stable. Okay. If it is a good reducing agent, means it has to lose its electron. Thallium 3 plus will lose 2 electron or 3 electron, and it has to be converted to thallium 5 plus or 6 plus. So that is not the case, right? So it will always try to accept the electron and act as a good oxidizing agent, not as reducing agent. So that is the incorrect statement. All other statements are correct. Okay, aluminium is more electropositive than thallium. Yeah, on moving down the group, electronegativity decreases and electropositivity increases. Okay. So those are the exception for that group 13. So all others are correct. Only the second statement is incorrect. Now let us see one more question. The molar conductance of 3 compounds are given at infinite dilution. And we have to find out the molar conductance of acetic acid at infinite dilution. It is very easy and very important formula. I'll tell you how to solve it. According to Kohlrausch law, at infinite dilution, here for the given species, CH3COOH plus NaCl gives CH3CO minus Na plus and HCl. So this is the equation. And here we are asked to find out the molar conductance of acetic acid. So let me take it as X. And for NaCl, what is the value? It is 126.45. And this is giving 91.0 plus 426.16, right? X is equal to 91 plus 426.16 minus 126.45. So when you solve this, you will get 390. You will get 390.71. Okay. So this is the answer. Option C is the correct answer. Got it? Option C is the correct answer for this question. Now moving on to the next question. The molar conductance of an electrolyte increase with dilution according to the equation, yeah, that we know, and we have to find out the correct statement. Which of the following statements are true? So statement 1 says that this equation applies to both strong and weak electrolyte. No, it applies only for strong electrolyte. So first statement is incorrect. Value of the constant A, that is the slope value, depends upon the nature of the solvent. Yeah, that is correct. It depends on the nature of the solvent. It varies with the solvent. Value of constant A is same for both the species. Value is same for both. No, BaCl2, if I separate this, I will get barium 2 plus ion and 2Cl minus ion. And if I separate MgSO4, what I will get? I will get Mg2 plus and SO4 2 minus, right? So here the value is not same. Here 2 plus 1 and 1 plus 1. It cannot be same. But whereas for magnesium hydroxide, what we get, the separation will be like magnesium 2 plus and 2 OH minus, right? So here we are having 2 plus 1. Here we are having 2 plus 1. So it is same for barium chloride and magnesium hydroxide, as the values comes out to be 1, 2 and 1, 2. So value of constant will be same for barium chloride and magnesium hydroxide and not for magnesium sulfate. So the statement is incorrect and the statement is correct. So the correct answer is option D, in which B and D are correct. Okay. Now let us move on to one more question. JEE question of this year. The resistivity of a 0.8 molar solution of an electrolyte is given and its molar conductivity is. So we have to find out the molar conductivity. So what is the formula? Lambda m is equal to 1 by rho I can put in place of kappa into 1000 by m. Because resistivity value is given, no? So in place of kappa, I can substitute this. So resistivity is this. This is nothing but rho. It is 5 into 10 power minus 3 into 1000 molarity. Molarity concentration is also given. It is 0.8 molar. So on substituting and solving, we will get 25 into 10 to the power 4 per ohm centimeter square per mole. Okay. So the correct answer is 25. Got it? Now let us solve one more question. The correct value of cell potential in volt for the reaction that occurs when the following two half cells are connected is, two half cells are given. One is oxidation and the other one is reduction. So oxidation occurs at anode and here is the cathode. So we have to find out the cell potential, that is E naught cell we have to find out. Okay, it will be cathode minus E naught of anode. So value of cathode is plus 1.33 minus of 0.44. It is equal to plus 1.77 volt. The correct answer is option A. Okay. Then coming to the next question, the conductivity of centimolar solution of KCl at 25 degrees Celsius is 0.0210 per ounce per centimeter. And the resistance of the cell containing the solution at 25 degrees Celsius is 60 ohm. The value of cell constant is. So what is cell constant? It is L by A. So L by A we have to find out. Excuse me. Here, centimolar solution is given. Centimolar solution is given. Centimolar means it is 1 by 100, right? So 1 by 100 molar, so it is equal to 0.01 molar. And the conductivity, kappa value, it is given as 0.0210 per ohm per centimeter. And the resistance equal to 60 ohm. We know that kappa is equal to 1 by resistance into the cell constant L by A. Right? Kappa is 0.0210, which is equal to 1 by 60 into L by A. From this, L by A is equal to 1.26 centimeter inverse. Cell constant is equal to 1.26. Just substitute in the formula, you will get the answer. The answer is option B. Okay. Now we will move on to one more question. So it is an assertion reason type question. So assertion says that in equation delta G is equal to minus N of E cell, the value of delta G depends on N. That is correct. And E cell is an intensive property and delta G is an extensive property. Yeah. What are intensive and extensive? Extensive properties are the systems which depends on the amount of the substance or whose value changes on changing the size of the system. Those properties are called as extensive property. And intensive properties are the properties whose value does not change on changing the size of the system. So here delta G is given as an extensive property. Yeah, because it depends on the number of electrons transferred in that cell reaction. Okay, because it is depend. You see here, it is equal to minus N. N means number of electrons lost or gained. So it depends on the number of electrons lost or gained. So it is an extensive property, and E cell is an intensive property. It is not going to change, even if I change the amount of the substance. Okay, so both are correct. So both A and R are true, and R is the correct explanation of A. So option D is the correct answer for this question. And coming to the next question, the two half cell reactions are given. We have to find out the standard electromotive force of a cell with feasible redox reaction. Standard EMF of the cell we have to find. So here you see two E naught values are there. The for first one, cobalt 2 plus 3 plus is equal to minus 1.81, and for aluminium to aluminium 3 plus, for that cell, for that couple, it is plus 1.66 volt. Since the oxidation potential of aluminium is more than the oxidation potential of cobalt 2 plus, so at anode, aluminium will oxidize, and at a cathode, cobalt 3 plus will reduce. That is the meaning, right? Since the E naught oxidation potential of aluminium is more than cobalt 2 plus, so at anode, At anode, aluminium will get oxidized. Okay. And at cathode, cobalt 3 plus will get reduced. Okay. So E naught cell is equal to E naught of cathode, cathodic reduction potential, minus E naught of anodic reduction potential. Okay, so you see here cathode reduction. So what I have to do, I have to go for the reduction thing. That is 3 plus bar 2 plus minus, in anode oxidation occurs reduction potential, no? So I have to go for aluminum 3 plus versus aluminum. So here the value is, so 3 plus 2, 2 plus ratio, right? So here 2 plus 2, 3 plus ratio. So I have to change the sign, change it to 1.81 minus 3 plus 2 aluminum. But aluminum to 3 plus is given. So change the sign from positive to negative and it will be equal to plus 3.47 volt. Okay. Got it? So in the question, oxidation potential is given. So we are finding the values in terms of reduction potential by using this formula. So option D is coming out to be the correct answer. And that is the E naught cell for the given reaction. Okay. Yeah, we will move on with one more question. For the galvanic cell, zinc plus copper 2 plus giving zinc 2 plus and copper, E naught E cell value is dash. We have some values in the question and we have to find out the E cell. So from the Nernst equation, we know that E cell is equal to E naught cell minus 0.059 divided by N into log Q. Right. And how to find out Q? Q is the oxidized ion concentration by the reduction ion concentration, right? So Q is going to be the concentration of zinc 2 plus is 0.04 and for copper it is 0.02. So the answer is going to be 2. Now substitute here. So E naught cell, to find out the E naught cell, we have to add these two, 0.34 plus 0.76 will give us 1.1 volt. So that is 1.1 here and here it is 0.059 by N. N is the number of electrons lost or gained. 2 electrons are lost for zinc, right? And 2 electrons are gained by copper. So the value of N is 2 and the value of Q is also 2. Log 2 is equal to 0.3. Now if we substitute and if we try to get the answer, we will get 109 into 10 power minus 2 volt as the E cell value for the question. So 109 will be the answer. Got it? Fine. Let's discuss one more question. Standard electrode potential for the cell is given in the question. Oh yeah, it is same as that of the previous question. But we have to find out the standard Gibbs free energy. Standard Gibbs energy we have to find out. So the relation which relates the standard Gibbs free energy and E cell is, it is equal to minus NF E naught cell. So this is a relation. Number of electrons lost is 2 and the Faraday's constant is given here. It is 96,487 and the E naught cell value is also given as 1.1. Just multiply everything. We will get 212271.4 joule per mole. In terms of kilojoule per mole, 212.27 kilojoule per mole will be the answer for delta G. Just direct substitution on this formula. Okay, option C is coming out to be the correct answer. Got it? Now moving on to one more question. Find the EMF of the cell in which the following reaction takes place. So nickel silver reaction is given. We have to find out E cell. So again we are going to use the Nernst equation in which the E cell is equal to E naught cell minus this minus E naught cell minus 0.059 divided by N into log of the oxidized ion minus reduced ion. But it is 2, stoichiometric coefficient is 2. So put 2 in the power. And here E naught value is 10.5 minus 0.059 divided by number of electrons lost is 2 into log of concentration of nickel 2 plus is 0.001. I can put it as 10 power minus 3 and here 10 power minus 3 square. It is 10 power minus 6. So the 3 gets cancelled and one more 10 power minus 3 will be there in the denominator. It goes to the numerator. So I will get 10 power 10.5 minus 0.0295 into log of 10 power 3. So here I have to use, when log of m to the power is there, I have to go for n into log of m, right? So this is the relation. So here I'm having log of 10 to the power 3. So it is 3 into log 10. So log 10 value is 1. So the final answer is 3. 10.5 minus 0.0295 into 3 is coming out to be 10.5 minus 0.0885. So the finally, when you subtract these two, 10.4115 volt will be the answer. Okay, 10.4. Yeah, sorry. It is not 10 point, it is 1 point. Okay. When we subtract, we will get option A as the correct answer for this. Got it? And 10.5 minus 0.08 is 10.4 volt. It is actually 10.4. It is not 1.0. Just give me a second. Yeah, it is actually, answer wrong here. It is actually 10.4115 volt. Okay. So that is the correct answer. Thank you so much, students, for listening the lecture. So we will meet up with the next lesson in the next session. Okay, thank you. Take care. Bye-bye.